Hi, in this video I'm going to talk about some of the result that we got in section 9.2, which is the introduction of the series and the geometric series and convergence of the geometric series and the divergence test. Okay, so the nth term test for the divergence, and then we will start section 9.3. okay, so in the last video we discussed about what is the series. So series is the sum of infinite sequence, that is called the series. Okay, if you add a sequence of infinitely many terms, then that becomes the series. So n runs from 1 through infinity. So if you plug in n equals to 1, you will get a1, and then this summation is plus, right? N equals to 2, that becomes a2. N equals 3, that becomes a3, and so on. Okay, so the next thing is, what is the partial sums? So why do we need the partial sums of a sequence? Is to define the convergence of a series. Okay, so we'll need the sequence of partial sum later, but first, what is the partial sum? So the partial sum is the sum of sum of only few terms, so in a certain order, okay, in a certain way. So S1 is just the first term, or the sum of that many terms from the beginning. Okay, S1 is just A1, S2 is A1 plus A2. So you start from the very beginning, and then so whenever you do S2, you go through the second term. Okay, if there is S3, you go A1, A2, A3. If it is S4, then it will be A1, A2, A3, A4. You go up to fourth term, up to that term. So what will be the Sn then? Sn will be A1 plus A2 plus A3 plus, and you keep going, and then you stop at nth term, right? That is Sn. So that's the sum of the partial terms, right? Now you see that there is a sequence now. It is like, the sequence is like S1, S2, S3, S4, and so on, right? And here you see that the S1 has the sum of the only first term, right? Or only the first term. S2 is sum of the first two terms. S3 is sum of the first three terms. So S1, S2, S3, S4, these are the sequence of sum of the terms. Okay, so S2 has more terms, some of the more terms than S1. So S3 has some of the more terms than S2, and so on. Okay, now if a sequence of partial sums, if that sequence of Sn, you can denote this by just Sn, right? If the sequence Sn of the partial sum converges to a number S, or converges to a sum S, that if that converges, then this series converges to S. That's the result. Okay, so to check if the series converges, or if the series has finite sum or not, what you can do is you can basically list the S1, S2, S3, and then find out the sequence Sn, partial sum Sn, and then see if that sequence of the partial sum, or if the sequence Sn converges to a number S or not. If it converges to number S, then the series converges to S. You see that the series has the sum S. If that sequence diverges, then the series diverges. Okay, if Sn diverges, if the sequence Sn of the partial sums diverges, then the series also diverges, meaning it doesn't have a finite sum. Okay, it's starting from 1 through infinity. Okay, so the next thing we discussed in the last videos is the geometric series. The series A plus AR plus AR squared plus, and then continue that way in the summation form. N runs from 0 to infinity. A times R to the n with R not equals to 0 is called geometric series. Okay, so the geometric series start from 0. You see that n equals to 0 to infinity. If you plug in 0 for n, what do you get? A times R to the 0, that will be just A. That's what the first term is, right? If you plug in n equals to 1, you will get A R to the 1, that is AR, that is the second term. The third term will be, plug in n equals to 2, will give you the third term here. So this series is called geometric series, where the common ratio is R, okay, and it should not be 0. R is called the common ratio. Now, if a series is given, how do you find out R? To find out R, you can do T2 over T1. What is the T2? What is the second term? AR over, what is the first term? T1 is the first term, that is A. So that if you cancel A and A, then what is left is R, right? So to find out the common ratio, you can divide the second term by the first term or third term by the second term. Basically, R is the ratio of the two successive terms. Okay, that's what the common ratio is. Now, there is the theorem related to the geometric series. The geometric series n equals to 0 to infinity ARn, that is the geometric series, diverges if R is absolute value of R is greater or equals to 1. What does that mean? That means absolute value of R greater than or equals to 1 means R is greater than or equals to 1, or R is less or equals to -1. That's what it means. Okay, that's what this means. So the geometric series diverges if the common ratio is either bigger than 1 or smaller than -1. If the common ratio is outside -1 and +1 interval, then the series diverges. Okay, or if R, absolute value of R is less than 1, that means what? R is between -1 and 1, excluding the boundary. Okay, or you can say that if -1 is less than R is less than +1, if the common ratio is between -1 and +1, then the series converges. Okay, if the common ratio is outside -1 and +1, including -1 and +1, then it diverges. If it is inside in that interval, then the series diverges. Now, what is the number? What is the sum then? If it diverges, that means the summation is a finite number. The sum of the terms is the finite number. What is that? That is A over 1 minus R. A is the first term, 1 minus R is the second term. R is the common ratio. Okay, so A over 1 minus R. All right, that is n equals to 0 to infinity AR to the n is equals to A over 1 minus R. Okay, guys. Now, sometimes you may sometimes the question may be like this: find the sum of, let's say, n equals to 1 through infinity. Okay, 1 through infinity, and then that might give you, let's say, 1/2 to the n. Okay, so you may be asked to find out that. Okay, so what is R here? R is 1/2, because if you compare that with this one, A is 1 times R to the n. So R is 1/2, right? Which is less than 1, so it has a finite sum. But the thing here is, so you see that this geometry series start from n equals to 0, but this one start from n equals to 1. Okay, so how do I make that starting from n equals to 0? You can write like this. So what is, if n equals to 0, what that terms will be? That will be 1, right? So what I'm going to do here is I'm going to write n equals to 0 to infinity 1/2 to the n. So I added extra term here, right? Because n equals to 0, I started from n equals to 1. If n equals to 0, that term will be 1, because 1/2 to the 0 will be 1. That is the extra term I added. So I want to subtract that 1 to balance. You see that? When you start from this one, in other words, you can see this one like this. You can see that, for example, that the left, this series will look like this: 1/2 plus 1/2 to the 2 plus 1 to the 1/2 to the 3, like that. 1/2 to the 3 and 1 over 2 to the 3 are the same thing. But here, what is that? I started from 0 because I want to use that theorem, right? So it's to start from 0 to use that formula. So what does that look like then? That will look like 1, because when you plug in n equals to 0, you will get 1, plus 1/2. When you plug in n equals to 1, you will get 1/2 plus 1 over 2 to the square, plus, and so on. Now, what do I get here? I got one extra term in the summation. Now, if I subtract that term, the extra term, then it will be equal to the one, this one, right? It will be equal to that one. You see that? That term, if you subtract 1. That's what I subtracted. Now, you see that the first one is the geometric series, right? Because it started from 0. So it is the geometric series. It has the sum. What is the sum of that geometric series? A is 1 over 1 minus R. that is a over 1 minus r. Okay, r is 1/2 minus 1. You see that? What do you get there? So 1 over 1 minus 1/2 is what? It is 1 over 1/2. 1 over 1/2 is 2 minus 1. So the final answer is 1 here. You see that the sum of this geometric series that started from 1, this geometric series is basically 1. Okay, so if it start from 0, if the question was starting from 0, that would be 2, but since it is starting from 1, that is just 1, because to make it geometric series you have to subtract 1 and add 1 on that, so that it starts from 0. Okay, so you should be careful on the where the summation starts also, okay, because it should start from 0 to use the formula for the geometric series. That is the another thing there. And next theorem is the divergence, the nth term test for the divergence. Okay, you should be careful about the converse of this theorem. So what it says is nth term test for divergence. It says that for a series n equals to 1 through infinity, you see that geometric series start from 0, but the general infinite series we are starting from 1. Okay, for n equals to 1 through infinity, an, for this series, if the nth term has the limit non-zero limit, meaning if limit n tends to infinity an, if the nth term has a non-zero limit, if the limit is not 0, then the series diverges. Meaning that if you are testing whether a series converges or diverges, what you can do is you can find out the nth term and then take the limit of that nth term. If you can find out the limit of the nth term, if the limit of the nth term is not 0, then the series diverges. Okay, in other words, if a series converges, then the nth term must have the limit 0. If the series converges, then the nth term must have the limit 0. But the converse of this is not true. That means if the nth term is 0, that does not imply that the series converges. Okay, if the nth term has limit 0, it does not imply that the series converges. For example, this series n equals to 1 through infinity 1 over n, the nth term is 0, right? If it was non-zero, then you could say it diverged, but nth term equals to 0 does not imply the series converges. So let us see. So here the nth term is 0, so we cannot use divergence test because divergence test does not imply. Why? Because the nth term is 0. The divergence test says that if the nth term is not 0, then the series diverges, but since the nth term is 0, then we cannot say whether the series converges or diverges. Okay, because so we cannot use divergence theorem to say that the series diverges, so we'll have to use different theorem for that. Okay, so we will discuss this type of problem in section 9.3. okay, so the integral test and the p series. So we will first define a theorem on the integral test. What does that mean? Okay, so here let us talk about the theorem here. So theorem is, suppose an is the nth term of the series, and then suppose that an I am writing using a function of n for that. Okay, the term an you can write as a function of n is a continuous non-negative function which is decreasing for x greater or equals to 1. Suppose that a sub n, which is denoted by f's function of n, f of n, is a continuous function and non-negative function which is decreasing. Suppose it is decreasing as well for x greater or equals to 1. Okay, how do I know it is decreasing? You can find out the derivative of that function, and if the derivative is negative, then it is decreasing, right, for x greater or equals to 1. Then the series n equals to 1 through infinity an converges if and only if the 1 through the integral converges, and if the integral diverges, then the series diverges. If the integral converges, then the series will converge. Okay, so that's what the theorem is saying. Now what I'm going to do is I am going to do some examples to use that. Okay guys, all right, let us see examples. Okay, the first example says, does n equals to 1 through infinity n over n square plus 1 converge? Okay, So first of all, to use this theorem, that we got this theorem, right? So to use this theorem, right, what does it say? Suppose that an equals to fn is a continuous non-negative function which is decreasing for x greater or equals to 1. Actually, you don't have to have 1, you can have any positive number there, okay? So x can be greater or equals to a, any number a there. We will discuss that later. And then you can start from that value, okay? That if you start from a number, let's say b, then you can write n equals to b through infinity. You can do that too, okay, for any number b. But for now, since this summation starts from 1, now we want to apply that theorem here. So this series converges if that integral converges, or this series diverges if that integral diverges. So they converge and diverge together, okay? So but this function, that an, that guy must be continuous, non-negative, and decreasing. That's the 3 things you need, okay? So this function fx, let f of x is equals to, it is like an, this is an, right? So we are denoting that by fn. What is fn? Fn is n over n square plus 1, which I denote. An is denoted by fn. But if I replace that fn by fx, okay, this is like fn, right? So what it will be? Fx, x over x squared plus 1. Okay, now, is this function continuous? Yes, this is continuous function. There is no break, because you see that for any value of x, this will not make the denominator 0. This will not be, there is no break, okay? There is no vertical asymptote. So it is continuous. Is this non-negative? Yes, for all n greater or equals to 1. So fx is continuous, okay? Non-negative. For all n greater or equals to 1, it is non-negative. And is it decreasing? And to check the decreasing, you can find out f prime of x. What is f prime of x? You need to use the quotient rule, right? So it is like the u over v. What is the derivative of u over v? It is derivative of v. So derivative of u times v, x squared plus 1, minus u is x times derivative of v is 2x, right? Divide by what? Divide by the v square is x squared plus 1 square. I'm just using the quotient rule there. So what do you get? X squared plus 1 minus 2x squared divided by x squared plus 1 square. So what do you get? That is basically negative x squared plus 1, or 1 minus x squared, right? Divided by x squared plus 1 square. Look at this. What are the values of x here? So we are saying that x, n is equals to 1 through infinity, meaning n is greater or equals to 1, right? So this function is, if x is greater than 1, this function, this value is negative. If this x is greater than 1, this value is negative. So which is negative for x is greater than 1. You see that? This is negative for x is greater than 1, okay? Or if it is equals to 1, what do you get? You will get 0 there, right? So we are saying that decreasing. So meaning that if x is greater or equals to 1, negative or 0, right? That is f of x is decreasing, f of x is decreasing for x is greater or equals to 1. Okay, guys. Now what we can say, we can use this theorem, this theorem. Now what you can do is to find out if this converges or diverges, then we can find out the integral, okay? Then by integral test, we can check the convergence of the integral. So we don't have to check the convergence of this series, because that is the same thing of checking the convergence of the series and the convergence of the integral. Okay, now by the integral test we can do 1 through infinity, right? And then you can do x over x squared plus 1 dx. Let us see if this converges or diverges. So how do I find out that? You can do the limit, okay, limit r tends to infinity, okay, 1 through r, x over x squared plus 1 dx. Now you can do that the denominator as u, and then that will be the numerator, and then dx will be du, 1/2 du. Or you can do, what is the derivative of the denominator? So the derivative of denominator is 2x, right? So you can write 2 times 1/2 times 2, so that the derivative you can write in the log format, because if the derivative of the denominator is the numerator, you can write log of that, right? So you can do u substitution if you want to, okay? Or you can do just the direct way, because I want to make the derivative of the denominator in the numerator, so that you can write the log of the denominator, okay? So you can write 1/2 limit r tends to infinity, right? And then you can write natural log of x squared plus 1, and the limits are 1 through r, okay? Now how do I do that? 1/2 limit r tends to infinity, okay? And then plug in the upper limit, you get natural log of r squared plus 1 minus natural log of 2, because if you plug in 1, it will be 1 plus 1 will be 2. Now if you take the limit r tends to infinity, this become infinity, so basically this is infinity, right? Since this integral diverges, you see that I'm starting from 1, and because that was started from 1 there, the summation, the question was started from 1, so I'm starting from 1. If the question start from 2, you would start that integral from 2, okay? So that's what it works. So if it is like starting from b, then that will start from b in the theorem, okay? That's what I was saying. All right, so what happens here is, since the integral diverges, since this integral diverges, then the series diverges, okay? Hence the series n equals to 1 through infinity, n over n squared plus 1 diverges. Hence this series diverges, okay guys? So the next example that I'm doing is starting from 2, and as I said here, so it doesn't have to be greater or equals to 1. It could be any number. It could be 2, 3, 4, anything, okay? So what it says is x should be greater or equals to 1 there, okay? Meaning that it should start from at least, the summation should start from at least 1, okay? It could be 2, it could be 3, it could be 4, anything is good there, okay? So you see, if an equals to function of n is a continuous, if the function f, or if the term an, continuous non-negative function which is decreasing, we will have to check the decreasing as well. For x greater or equals to 1, meaning that 1 can be there, it could be 2, 3, 4, x, anything. So that's why it says greater or equals to 1, okay? It could be x greater or equals to a there, where a is greater or equals to 1, okay? That is fine. Then the series summation n equals to 1 through infinity, or it could be n equals to 2 through infinity, 3 to infinity, anything. That's why I'm saying b through infinity converges if and only if the integral starting from b through infinity, where b is greater than or equals to 1, okay? Fx dx converges, or if it diverges, if this integral diverges, that series will diverge as well. Let us do this example. Does this n equals to 2 through infinity 1 over n natural log of n, does this converge or diverge? Okay, let us do this. So solution, let f of x equals to 1 over, you replace n by x, okay, x ln x, okay, that is f of x. Is this function continuous? Yes, it is continuous. It is non-negative, okay, for n greater or equals to 2, okay, and it is also decreasing. How do I know that it is decreasing? You can find out the derivative. Okay, let us do that. So f of x is continuous, okay, and non-negative, and and what? F prime of x will be what? So you can, what is the derivative of that? It is, so this is like u over v, right? So you do derivative of u, that is 0 times v x ln x minus u is 1 times the derivative of v. What is the derivative of that? It is again the product rule there, right? That when you find the derivative of denominator, you will have to use the product rule. You can do x times 1 over x plus just natural log of x divide by x natural log of x square. So what do you get there? That the first term will be 0, and that one is negative 1 plus natural log of x divide by x natural log of x square. Okay, guys. So here, for which is less or equals to 0 for x is greater or equals to 2. You see that? We are taking n equals to 2, so n equals to 2, 3, 4, 5 like that. So I'm saying x is greater or equals to that number. You see that? For any value of x greater than 2, this function is continuous, because this function fx is not continuous at x equals to 0 and x equals to 1. Why? Because it will give you 1 over 0, that is infinity. Okay? So, and 1 over 0 for at x equals to 1, it is 1 over 0 infinity. But we are not worrying about x equals to 0 or 1. We are just looking at n greater or equals to 2. You see that? N equals to 2 here. So we are saying n is, the summation starts from 2. N equals to 2. Okay? So we are saying that's why for x is greater or equals to 2, this function is continuous. This function is non-negative. For x greater than 2, this will be always positive number. Actually, for x greater than 1, it is positive number. So it is definitely positive for x greater than 2, that natural log of x. Okay? And this is also this is also decreasing, because the first derivative is less or equals to 0. So f of x is also decreasing for x is greater or equals to 2. Okay, now what we can say is from this theorem, to know if the series converges or diverges, it is same as finding the limit of the finding the integral. Okay, improper integral. So let us find out let us find out that integral 2 through infinity. You see that since the summation starts from 2, I am just starting the integral from 2 to infinity 1 over x natural log of x dx. If this integral is finite, then this series converges. If this integral is infinite or diverges, then the series diverges. Okay? So how do I find out this? Is you just do the u substitution, right? How do I do the u substitution there? Let us try that. Let's say u equals to what? U equals to natural log of x, then du will be 1 over x dx. Okay? So what do you get there then? So you get that as equals to limit, because the improper integral, right? R tends to infinity, 2 to r, and then you can write that as, oh, by the way, you can just change the limit as well. So instead of doing 2 to r, say let's plug in the limit. When you plug in that x equals to 2, you will get u equals to natural log of 2, and then when you take x equals to infinity, I'm just changing the limit, then you will get u equals to infinity for x equals to 2 and infinity. Okay, so you can write natural log of 2, okay, and then infinity, so 1 over u du, that's what you get, right? So this is limit r tends to infinity, right? So what do? Now what is the integral of that? It is natural log of u, right? And then what are the limits? Natural log of 2 and then through infinity. Now plug in that limit r tends to infinity, natural log of infinity, right? Natural log of infinity minus natural log of 2. That's I plug in the limit, upper limit and lower limit. What do you get if r tends to, oh, by the way, this is not infinity, this should be r, right? I'm sorry about that. So this should be r there, because I'm writing r tends to infinity, r, and then r. So when you plug in r tends to infinity, this will become infinity, right? This is again becoming infinity. So this integral diverges this integral diverge means that series must diverge as well. Hence by integral test, the series summation n equals to 2 through infinity 1 over n natural log of n diverges. Okay, so we will see more example in the next video. Okay guys, all right.